Hello there, I'm Robert Feldt, and I will present a short paper that I've written together with my co-author Shin and friend Shin from KAIST in the Republic of Korea, and I'm from Chalmers University of Technology on the west coast in Sweden, in Northern Europe. Our paper is an argument for search-based software testing to lift our view and gaze up and try to search for and optimize flexible probabilistic models in order to then use these models to generate test data. And I'll give a very overview and short presentation of our argument here. So this is based on an observation. So we've seen that a lot of work in our field of SBST is often quite low level. It's on an atomic level. And the risk when we do that, so we search for a specific test datum, for example, is that we are too myopic. We're looking too far down. Let's say we have some system under test which can take differently shaped egg-shaped stuff in there. Quite a common way to use search-based software testing is to search for a specific new input here, right? So we tell SBST, some system that we have, some algorithm, please search for an input that, for example, crashes the soot or covers this specific branch or increases this metric by a certain amount and so on. So, for example, let's say we want to find so fill in the gap here, right? That's what we ask search-based software testing. So we want to find a particular input, like the golden egg, which fulfills our goal, right? So this is on an individual input data level, and this is quite commonly how it's done. This can then be used, of course, in a sequence. So in that way we are maybe looking for several of these inputs, but our focus is still on the individual. So sometimes, as I said, we go one level up and we are searching for a set or for a sequence, right? So one example would be SBST, please find a diverse set of test cases or test inputs. This is something I've focused a lot on before. So diversity tends to be good because if you have only a limited budget, you want to not use it to test similar things. So, find me, I don't know, what kind of budget do I have? I have a budget for 100 test runs. So find me 100 unique and diverse test inputs that, really exercises this piece of code as much as possible. So instead of finding like a set of common stuff, find me something diverse, something different. This sometimes happens. So now we're not doing it in sequence. We're not only focused on finding one input, but we're looking at optimizing the whole, so a set, which is fine. But rarely do we search for models, at least in our experience or reading of the field. So, and we think this is to our detriment. So, what we would tell SBST or our system in this type of use would be, please find me a generator, some kind of model of the test data that can then be used to generate some, realistic test data or crazy test data or test data on a border or test data that is different from what we've already used and so on, right? But the key thing is not the goal or the objective, but it's the kind of the shape of what we're trying to find. So find me the model, find me the generator, which I can then apply many, many times, right? A more even higher level would be find me a sequence of generators or a sequence of models or set of models that then can be used to generate, to fulfill my goal. For example, you can imagine, there have been these arguments that, for example, adaptive random testing, which is a type of diversity, it might not be so useful because it's very costly, right? To search for the next test data in the sequence that is different from what we already have. But of course, if you can do this offline up front, you will now have a setup, a sequence of models or generators, which you can then use live to generate the sequence that will then be, more diverse, give more diverse testing, right? So you can see there are levels here: the individual level, the set-based or sequence level, the model level, or even models of models, like sets of models that fulfill our properties. So we want to focus on these two in this argument. We think the community should focus more on these higher levels. So we argue we should be searching for flexible and probabilistic test generation models. So, given my argument so far, or our argument so far, we could use different models, right? Different forms of generators. But we think there's a lot of benefit into looking at flexible probabilistic models, because there's a lot of work on probabilistic models in deep learning, in AI, and in many other fields. There's a lot of theory and tooling around probabilistic models, so we think it's natural for us to try to leverage this. So this will put a new set of requirements on us. Probably we need to think about, do we separate the structure of the test data that we need to generate from the non-determinism, the sort of things that can be probabilistically governed, right? So structure can be things like input has a certain grammar, right? If an input field requires an email address, then we need to give our generators some kind of sense of that structure. So what does it mean to be a string which is a valid email address, right? This can be sort of a grammar, it can be a programming language, it can be different shapes to describe the structure. But we do think that if we can separate out this structure from the model that governs the probabilistic choices that we can then use to when we generate from this structure, then this can be beneficial, and we need to at least consider it. We also need probably new ways of expressing the non-determinism, the randomness, the sort of probabilistic choices in there. And then probably, since we change the separation and we change what it is we're going to look for, we might need new ways of searching and optimizing in our field. So one example can be generative probabilistic models. So this is, all the rage in, you've seen these deep fakes and all of these systems that use deep neural nets to generate realistic looking new images of celebrities that do not exist, for example. So the general idea there is a generative, as defined by Foster in this book, is that a generative model describes how a data set is generated in terms of a probabilistic model, and by sampling from that model, we can then generate new data. And we think this is a very natural fit for SBST. And of course, there's been several existing tries in this direction, but we do think that the community as a whole would benefit from considering this more. So in the paper we have a very simple conceptual model where we think there's some benefit in looking at these two different dimensions. So on the x-axis here we have the flexibility of the probabilistic modeling. So to the left on the x-axis you have random model. So that's no model, right? The non-determinism is somehow there and can affect what kind of test data is generated, but we don't really control it. And then we can go up, and I'll describe that more. But on the y-axis we have modeling types, so ways of doing this. And the first two on the y-axis are the integrated ones. So there it's hard to separate out the probabilistic model from the structure. So they are tied together. And one example of this can be quick check. So this is a random, it's based on random test data generation. So quick check is a property-based testing tool, which is quite famous. Nowadays probably you've heard about hypotheses, which is a Python implementation of this, but it's available for many languages. So QuickCheck in its basic form at least have manual integrated probabilistic test data generation models, and so they are random. So you can code them a little bit and make them more custom or introduce a certain distribution, but it's kind of hard coded in the code, and the structure and the probabilistic model or distribution is very tightly tied together in the code because you write your generator, right? So in principle, you can implement a Turing complete QuickCheck data generator, but the language doesn't really support it. You can write it yourself in Haskell or in Python or whatever. So some of these systems, they go one step up. So they are still integrated, so you don't separate out sort of the grammar or the structure of the data and the probabilistic choices, but they give some kind of support, so they can help you tune the distribution somehow a little bit, right? Then myself and others have worked on a system called Gödel test, which the main claim to fame there, or idea there, is to separate out the structure and the non-determinism. So here we see three different types of models, because since we separate them, we can, for the same structure, say we want to generate JSON files. So that gives us a structure. What is an allowed, valid JSON file? Then we can plug in different models, probabilistic models, and get different levels of flexibility in how we generate JSON files, right? So Gödel test is a search-based system. So once you have set up the structure, you have different ways of having local univariate choices. So those are choices in the grammar or in the structure which are local. So they don't look at the whole thing that you've generated so far, or they don't look into what you will generate next. They take a local probabilistic decision on what's being generated, right? So that's these models are what would be called factorized. So they are factored, so they are independent. The different choices are independent. So this gives a little bit more flexibility than having a random generation, of course. But what we found in Gödel test early on was that you need much more control. So we introduced something called depth varying probabilistic modeling, where you could use at least the depth. So how many times have I been in this position of the structure before, and then you can vary the probability distribution, which is still local, but you can vary it globally. So this is kind of going towards a more flexible probabilistic model. And then in some studies we use Monte Carlo tree search, which was made famous by AlphaZero or AlphaGo, the Go playing program by DeepMind. But early on we connected that to the Gödel test data generator, and then you can do joint distributions, and you can have global properties that affect the local choices that you make when generating test data. But and there are many more techniques and systems out there, of course. But here in this paper we propose a few new ones. So there's a whole set of programming languages called Probabilistic, and we argue they can be used to do automated tuning of probabilistic models. But since they are programming languages, they allow you to write a generator for test data and have the probability model spread out over that program. So it's still sort of an integrated way, but you have a powerful algorithms to tune that distribution. Another thing we can do, we can go more flexible on the Gödel test separation path. And there, for example, using something very powerful, like a Turing complete language for taking the probabilistic choices, could be to have a GP, a genetic programming way of getting the model. This is something we've written about before, but here we kind of explore the idea some more. And then the most flexible would be a fully Turing complete way of trying to search for also an integrated model, in an integrated model, but still allowing the probabilistic model to evolve together with the structure of the test data generator. So this could be, of course, implemented in a Turing complete GP piece of software, right? So we just try to paint a few of these possibilities here in this paper, and we really think there can be a lot of benefit, and these techniques can also go together with deep learning and the recent hype in AI. So we think it's a great opportunity for the field. Thank you.